Okay, so now we're going to move into a little bit more about how the periodic table was set up and how the atoms are set up. So up till now, we've talked a little bit about the structure of the atom. We've used Rutherford's model. Protons and neutrons are in the nucleus. The electrons travel outside. We're going to talk a lot about that. So if I have my positive charges here, and I have negative charges here, as the electrons are spinning around, why don't they collapse into the nucleus? Opposites attract, right? So that's kind of what we're going to get to, is why those electrons don't just fall into the nucleus, why they're not allowed to. And Bohr, Niels Bohr, attempted to address it using emission spectra. We did the lab with this in first year chem. In emission spectra, what you do is you shine light through a prism. If it's white light, it produces a continuous spectrum like a rainbow. If it comes from an electrically excited atom, it's not a continuous spectrum. It's only a few wavelengths that you're allowed to have. And the line spectrum of an element is unique to that element. It's kind of almost like a fingerprint. You can use it to identify the elements. So this is what white light does, the whole Roy G. Biv spectrum. And every color in here has its own unique wavelength. And because of the equation E equals hc over lambda, they all have their own unique energy. Every color, own wavelength, own energy. So if you look at emission spectrum, and the one that he looked at particularly was hydrogen. It didn't matter what kind of a sample of hydrogen you had, all the hydrogen atoms, when he electrically excited them in a tube, put it through a prism, he saw a purple light, a blue light, a green light, and a orange light, red light. And always at those same wavelengths. And because of this equation, E equals hc over lambda, they can determine the amount of energy associated with each one of those transitions. They all have a unique energy associated with those transitions, and it's always the same for hydrogen. And then if you look at other ones, Mercury's got different lines, and strontium, and then I've got like a whole sheet of them. Look at all these guys. They're all crazy all over the place. Sodium's heavy on the yellow. Helium's got kind of like a mix of everything, but hydrogen in particular has 4 lines. Okay, and so what he interpreted from this is because the atom has a nucleus in the center, and electrons orbiting in certain what he called orbits, and each orbit has a unique energy. So if you have your protons in here, you've got your orbits. And as the electrons gain or lose energy, they make a transition. This energy level and this energy level have 2 different energies. The farther away from the nucleus they are, the higher the energy is. And when it makes this transition, it gives off light with a certain wavelength and therefore a certain energy. And so those transitions are only allowed to have certain values. And the electron cannot collapse into the nucleus. Okay. When the atom is energized, you pop some electricity in, the electrons can jump up to a higher energy level or another higher energy level, or they could even go from 1 to 3, or they could go all the way up to like 4 or 5 or 6. And when the electrons return back down, they release energy with a specific energy and wavelength associated with it. Because every color transition for hydrogen, there's only 4. In the visible spectrum, there's only 4. And so they each have a unique wavelength. They each have a unique energy. That means those transitions have a unique energy involved. The bigger the transition, the more energy is involved. The higher the frequency, the shorter the wavelength, and the higher the energy involved. So if an electron takes on energy, it jumps up. It could jump from here to here, or it could jump from here to there. It could jump however it goes, okay? I want you to notice one thing in particular, that the circles, the orbits, are varying distances from each other. and I'll talk about that later. They're not all the same distance. This one versus this one versus this one. There's a different distance between all of them. When the electron drops back down, it releases light with a certain wavelength and therefore a certain energy that corresponds to that transition. So this transition from 3 to 2 is less energy than the transition from 2 to 1, which is way less energy than 3 to 1, which is way less energy than 4 to 1. Okay, the farther out it is, the bigger the transition, the more energy is released with it. So this is a picture of the different transitions for the hydrogen atom. It's not the same kind of circles. It should be. This is the one that we can see. It's called the Balmer series. It's in the visible spectrum. From energy level, if this is 2, 3, 4, 5, 6. From 6 to 2, the wavelength is 410 nanometers. That's in the purple spectrum. From 5 to 2, it's 434. That's in the blue part of the spectrum. 486 is from 4 to 2. And 3 to 2 is in red. That's 656. Okay, that's the only transitions because this is a bigger transition. It has more energy than this one. If it has more energy, it has a shorter wavelength. Okay, so Bohr determined the energy associated with each energy level using the equation before. So this is a constant. Z is the atomic number, and N is the principal quantum number. That is the energy level or the orbit, because remember back then they didn't have orbitals. But it only works for the hydrogen atom. So if I had to do the energy of level 1, it's at 2.178 E negative 18 times 1, because that's the atomic number, over the energy level squared. That's the energy of it. If I did level 2, it's 2.178 E to the negative 18, 1 over 2 squared, which is 1/4 of this number. If I did it for level 3, it's 1 over 3 squared, 1/9. That's why the circles get closer to each other, because the distance here is a factor of 1, this distance here is a factor of 1/4, the distance here is a factor of 1/9, and it keeps going 1/16. And as they get farther and farther apart, they get closer and closer together because it's this number, orbit, squared. Okay, as the electrons drop down, the energy of the photon that is emitted can be found by doing a calculation. Go ahead and write this down. I will give it to you. You do not even need to memorize it. This is how he calculated the energy that's involved, where delta E is the amount of energy that is associated with a photon of light. It can either be absorbed as the electron goes up, positive delta E, or released as the electron drops down, negative delta E. Ni is the energy level it starts at, and Nf is the energy level it ends up at. Okay? I'll give it to you. So, sample problem. Calculate the change in energy when a hydrogen atom electron drops from level 4 to level 3. So, go back. Delta E equals 2.178 E negative 18 times 1 over where it started, 4 squared, minus where it ends up, 2 squared. Okay, this part you can do in your calculator with parentheses. Multiply it all out, and you end up with a negative 4.08 E negative 19 joules. And it is negative because it's exothermic, because it went from 4 down to 2. It's exothermic. Okay? That's all the negative means. Okay, so now to calculate the change in energy needed to excite an electron. So we would expect this number to be positive. Delta E equals RH. It's not the same thing as the R from gas laws. Over 1 over 3 squared, times 1 over 3 squared, minus 1 over 6 squared. Do that math, and it ends up being 1.815 E to the negative 19 joules, and it is positive because this is endothermic, because the electron is being excited. Okay, now here's where we get into the real math. So calculate the wavelength of light produced when the electron drops from level 6 to level 3. So the wavelength of light, first thing I need to do is calculate the energy change. RH times 1 over 6 minus 1 over 3, both of them squared. If you notice, it's just the reverse of the previous problem, so the value here is now negative 1.815 E negative 19 joules. And it is negative because it is exothermic, because it's dropping the electron. Okay? Now I want to calculate the wavelength. Well, I know this equation, E equals hc over lambda, so I'm going to take that energy, and I'm just going to make it positive because it's the energy that's released. The only reason it's negative is energy is released. So 1.815 E negative 19 equals hc over lambda. Do the algebra, cross multiply, divide, whatever you need to do. You end up with a wavelength of 1.095 E negative 6 meters. Okay, that's probably in the infrared spectrum. But the big thing to recognize is this is delta E. It's an energy change between two different energy levels. This is the energy of one of the photons that comes off. And this wavelength, when it goes from level 6 down 4, 5, 4, 3, down to level 3, it releases light with a frequency of this, a wavelength of that. And it's not allowed to stop anywhere in between because that's the only energy it's allowed to have when it makes that transition. It's not allowed to stop in the middle somewhere. And so these energy levels are kind of like floors in a hotel. Okay, you can't spend the night in between the floors. Okay, you either have to be on the 3rd floor, the 4th floor, the 5th floor, or the 6th floor. It's the same kind of an idea. Okay, so Balmer series for hydrogen always ends at energy level 2. So what color of light would you expect to see if the electron drops from 4 to 2? So delta E equals RH times 1 over 4 squared minus 1 over 2 squared. Do that math. It ends up being negative 4.08 E negative 19 joules. To do E equals hc over lambda, we're going to make this positive because all it is the energy associated with one of those photons. .86 e to the negative 7 meters. I think if you Google that, you'll find out that it's in the yellow-green spectrum, probably heavier on the green. Okay, so I don't expect you guys to memorize the colors of the different wavelengths. That's really not expected. All right. So here's where it's really challenging. So they see a violet line for hydrogen. Since it's in the visible range as part of the Balmer series, that means NF is 2. From which level did the electron drop? So I know the light had that much wavelength. So the energy associated with that wave is hc over the wavelength. Keep it in meters. And that is 4.84 e to the negative 19 joules. That's the energy associated with the photon. So if I'm going to put it into the delta E equation, 1 over the energy level it started at minus 1 over 2 squared, because that's what the Balmer series means, I need to make sure that I recognize that that energy is being released. I need to put in the negative, or the math will not work. You're going to get an answer that makes no sense. Okay, so you set it up like this. First thing I would do is I would divide here. And when you do that, this goes away. You have 1 over x squared minus 1 over 4 equals some number. I don't know what it is off the top of my head. I would add 1/4 to it. You get 1 over x squared equals 1 over 36 x equals, take the square root, x is 6. Okay, you should always expect to get a whole number. It should be bigger than 2. Okay. This is the hard kind of problem. You have to really kind of know your stuff. The biggest thing is, if the electron dropped, you better make sure you put that negative in there, because that energy is being released. And if you don't, when you add 1/4 over, and this is a positive number, it doesn't work.